Our next presenter, somebody who has really helped us up the score in many ways over the last 3 or 4 years by bringing a high-level professional view to the kinds of things we can do as amateur radio astronomers. Dr. Wolfgang Herrmann from Astropeiler Stockert in Germany is on almost every SARA online session, and the kinds of inspirational guidance he gives us is tremendously appreciated. Now, he spent more time in the US than I have, I think, and I believe he's not offended if we call him Wolfgang, but would like to welcome him for this presentation. Thank you so much, Dr. Herrmann. Over to you.
Thank you very much, and welcome from my side. I'm looking forward to the talk, and as usual, the first try will be to get it shared. And now I need to get... So I hope everybody can see my screen, full screen now.
Jansky sees your screen.
Yeah, and online I hope as well.
Looks great.
Okay, thanks, Ted. All right, I would like to talk about fast radio bursts and magnetars, and especially what their relationship is, or potential relationship. But before I go into the subject, because we have quite a number of new members, let me just say a few words about Astropeiler and the instrument. It's actually a historical instrument in a certain sense, because it was built in 1956, so pretty old by now. And originally it was used by the Bonn University and later on by the Max Planck Institute. Max Planck Institute now actually operates a much bigger instrument, a 100-meter dish in Effelsberg. So when that was built, they turned it back to the university. They continued to use it, and finally it was decommissioned and sold in 1995. And that could almost have been the end of story, but it was by the initiative of a couple of people was declared a technical monument, sort of to keep it in a way. But the real story now starts in 2005, when the whole campus was acquired by a foundation. And the important thing was that this foundation provided the funds to renovate it and put it back into operation. That took quite some time. That was done in the years until 2009, and in 2011 we saw first light with a new instrumentation. So we didn't keep the old instrument. It was completely refurbished with modern instrumentation. Quick story about the two organizations in the background. I mentioned the owner. That's called Nordrhein-Westfalen Stiftung, North Rhine-Westphalia Foundation. And it's not a science foundation, something like that, but they're in the area of preserving things of nature and also of culture, and that is considered as a technical culture. And on the other side, there's ourselves, a volunteer organization which actually maintains and operates the instrument and does all the further development. And it was founded in 1995, so quite some time ago, with sort of a vague idea, maybe to keep the instrument for posterity and maybe opening for the public again. And that was actually achieved. And is even more surprising is that we were able to bring it back to scientific operation. But of course, education and outreach are a main part of our work. This is all done by volunteers. Nobody gets paid for it. The payment is the fun that we have with it, and it's really great fun operating this instrument. So let's go into the things that we do, and really our favorite subject are magnetars and fast radio bursts. Because that's our favorite subject, we really like to talk about it, and I have talked about this even several times during SARA conferences. The first time That was in 2021 when I talked about our first fast radio burst observations. So we were very proud at the time that we were able to actually receive those. The year after, on the Western Conference, I talked about a different but somehow related subject, magnetars. And I'll talk about that in just a minute. And then last year in 2023, we had a bit more to tell about the details of the observation campaigns of one fast radio burst. So we talked about a lot about it already. So why talk about it again? What is the motivation to bring the same old story back up again? Now, the motivation for this talk is that we now have concluded what we have found on the Magnetar. That's sort of the final findings I would like to talk about, and the findings from the paper that has been published. And the same goes for one of the FRBs, where I also talk about the final findings and also what's the sort of the essence of the scientific paper that we have written. And then, of course, we went on and observed more fast radio bursts. And the background of question that is really of interest for us is the question, are magnetars the progenitor of FRB? So what is the relationship between those two? Can one draw a conclusion? And that will be sort of also the conclusion of my talk today. So let's go into the magnetars. What are magnetars? Magnetars are just like pulsars, they are neutron stars. But what differentiates them from pulsars is that they have an extremely high magnetic field. I mean, pulsars already have a very high magnetic field, but here we're talking objects that have about 1,000 times stronger magnetic field than a pulsar. How that comes about, there are two theories. I won't go into that. Nobody knows exactly what the background is, but which of the two theories is true. But anyway, they have a strong magnetic field. Typically, they have a low rotation rate compared to pulsars. They are typically larger than a second, whereas we have, for pulsars, we have a few hundred milliseconds typically. They have a high spin down, that is, they lose energy, the rotation rate goes down. High means 10 to the minus 11, which doesn't seem very much, but a average pulsar is in the order of 10 to the minus 15. Magnetars typically show in X-ray and gamma emission, and sometimes they are flaring. And only a few are actually visible in the radio regime. So most of them are just showing up in X-ray and gamma. When they have radio emission, they have a highly polarized emission, linear polarization, and they have what is called a flat spectral index. So the intensity doesn't change very much with the frequency. As of today, there are not that many magnetars that are known. There are 31, and only 6 of them are actually active in the radio regime. So quite exotic objects that are there. If you think about, there are about 100 billion stars, but we only know 6 radioactive magnetars. So what we have done, the whole story started when there was an astronomer's telegram that indicated that this magnetar, which had been active and had disappeared, had become active again. And that really was a high motivation for us. When we saw the astronomer's telegram, we just went ahead and observed it and immediately were successful. What I'm showing here on the left side is a so-called Presto plot. So this is the same type of plot as you would see from a pulsar. So you see the 2 times the pulse here. It's a rotating object, just like pulsars. I mentioned the low rotation rate. This one has a rotation about 5.5 seconds. So slowly spinning around. Now, what is interesting about magnetars, and that's also potential relationship to FRBs, is that they every now and then emit bright single pulses. And I'm showing here on the right side one of those bright single pulses. The characteristic here is that in this kind of waterfall diagram, you see the vertical scale is the frequency, and horizontal, obviously, the time. And you see it's spread over a wide frequency range. In our case, we are observing in the range from 1330 to 1430 megahertz. So it covers all the band and emits there. So these bright single pulses were of specific interest. We have more than 1,000 hours of observation. So we were both monitoring the profile and the single pulses. And there was something interesting that we saw. The top graph here shows how did the flux density, so the average energy of the magnetar develop over time. You see there is a decrease over time, and then therefore we sort of stopped observation. And then there was a second phase when it came up again, another episode of activity, and then we had relatively high flux densities. These are, to those of you who are familiar with the pulsars, the strongest pulsar in the northern hemisphere, that's about a third to a quarter of that, so quite intense. Now, on the bottom line, you see the single pulses, number of single pulses that we've observed in each of these observing, and there were just a few. That means every couple of days we saw a single pulse. And that changed dramatically during the second part, during the second observation episode, where we had an extremely high number of single pulses, which we could detect. There were in the order of a couple of hundred per hour. So very, very many very bright single pulses, even though the average intensity, yes, it did go up, but not by a drastic factor, maybe factor of 3 or so, compared this one to here. But the number of single pulses was dramatically increased. So there are really two phases that we have observed. One is nice profile, and every now and then a intense single pulse, and then a second phase, a second period when we saw, again, a high activity in the average, but an extremely high activity in single pulses. So what is the main takeaway from this magnetar observation? 5.4 seconds, many bright single pulses. Over the time, we have detected something 150,000 single pulses. We've seen, as I mentioned, high and low activity. All the single pulses occurred exactly at the phase of the average profile. So they were also coming in that, let's say, 5-second interval. The single pulses were in various shapes. They were double pulses, triple pulses, single pulses, whatever. Almost anything you can think of, we saw. And that did change over time. I can't go into the details of that. The main point really here is the number of pulses, single pulses, sort of generally correlate with the average flux density, but there are these two different phases, which I have explained. Another important thing which I want to point out, all the single pulses cover the full frequency band of our telescope, the 100 megahertz. There was no clear detection of what is called a sad trombone. A sad trombone is something when you have multiple pulses and they change their frequency allocations, and that doesn't happen. What we did observe was an occurrence of a sudden dropout. So all of a sudden, it was as if it was gone for one day. We can only observe that during a certain time of the day, and all of a sudden it was gone one day, and then it was back again the next day. And it was not an instrumental effect. So these are the main things. If you want to really get the full story, we have published a paper that's available. It can be downloaded freely, and I've given here the reference. Okay, so this is the observation that we have in the past and what we have published. Now, we recently observed a rebrightening in June, and we did 80 hours over 3 weeks. And there were just a short episode where we again saw a high pulse activity, single pulse activity. And then it sort of went away. One important thing was that because we had this high activity, we asked another telescope, the Effelsberg telescope, to have a look at it as well. And they have a very broadband receiver. And the finding was that the observation, the emission of that magnetar is really very, very broadband. And I'll come back to that later on. All right, fast radio bursts. What are fast radio bursts? These are, as the name says, a fast burst in the millisecond range. They appear with a very high dispersion, which means they have traveled a long distance. The first fast radio burst was discovered by Duncan Lorimer. It's a so-called Lorimer burst, which created a lot of excitement. I cannot talk about too much of a background here. But anyway, the key message is these are single pulses. They come from far away from other galaxies, 1 billion light years away. So they must be very, very intense. Now, the dispersion that gives rise to the idea why they are so far away, that's called by charged particles, electrons in the space between the source and the telescope. So you have somewhere in a different galaxy, you have your fast radio burst source, and then it travels along, and it is not empty space. There are some electrons which give rise to a dispersion. So dispersion means higher frequencies travel faster than lower frequencies, though the lower frequencies are a little bit delayed. It's a very small delay, but noticeable. And the main story is this delay cannot be caused by our own galaxy. Electrons are not enough there, so it must come from far away. And this is really the main message here, very far away. So what are these? We know the phenomenon, but we really don't know the source. It was thought to be just a one-time event because one saw a pulse and never did not occur again unless one day one was detected, which actually did repeat. That was detected by Laura Spittler, famous detection. And ever since then, more repeaters have been detected. And very much like the magnetars, they show an episodic behavior. So they come and then they go. So you see them for a certain period of time and then they're again away. What we did with FRBs is we started the whole story when there was a astronomer's telegram, which was published by the CHIME Corporation. And they had observed a repeating fast radio burst. And then it was reported by various other telescopes. I have listed them here, that there were reported detections by quite a number of telescopes. So we thought, well, let's give it a try, especially because we had reported that they were in a range of the fluence which was strong enough for us. So that's what we did. And in fact, it took us a while, 90 hours. And after 90 hours of observation, we actually had our first fast radio burst, which is shown here. Again, what you see is the pulse itself. It is a dispersed graph. And again, the frequency here. And it's, as you can see, covering the whole frequency range with drops in between, which are caused by scintillation. Now, this observation that started a cooperation between ourselves and 3 other telescopes of approximately the same size, and 25-meter dish in Westerbork in the Netherlands, a 30-meter dish in Torun in Poland, and the Onsala telescope, again 25-meter in Sweden. So we joined forces and we did joint observations, and we picked that FRB that I had just mentioned. And we did an observation campaign, which is sort of summarized here. It requires a little bit of explanation. So each of the vertical lines is a observation, which time is covered. The violet ones are our observations, and the spectral range is given here. So the vertical line is the frequency range. So there are some by Turun which are in the S band in the 4 point something gigahertz range. Most of the others are in the L band, and then there are some observations in the P band around 300 megahertz. So these are all the observations, one observation period and another observation period in the 21 to 22, and here up to 2022 March. The black vertical lines are actual FRB detections. So this is what we have done. This is what we have detected. And you can also see a bit of an episodic behavior. We had many pulses, or rather many pulses here, just a few there, in between silence. So again, episodic behavior. So this whole observation effort were more than 1,400 hours of observation time from our telescope. And if you count them all together, these were 3,500 hours of observation times. We ourselves have detected 16 bursts during this time. So if you think about it, 1,400 hours and only 16 bursts, that's a lot of effort for just a few bursts. There were 46 from old telescopes. And if you take all the data together, we have published a paper on that. Is given here, the reference. Again, this is a freely accessible publication in Nature Astronomy. So if you want to look it up, you can actually download it. Lots of things are discussed in that paper. And I really would like to go and highlight two things here. Of course, there were observations of this source by other observatories, large dishes like the FAST 500-meter dish FAST in China. They observed it, and of course, because of the higher sensitivity, they see much more pulses. We only see the tip of the iceberg, the real energetic ones. And the interesting piece is if you extrapolate the energy, or how frequently occurs which energy, over the energy range that these telescopes cover, and if you try to extrapolate that, you would expect much fewer pulses than we have actually detected. So what we find is that there's a break in the distribution. So the higher energy pulses are actually more frequently than expected. The interesting thing about that is I have to go back, make one more comment about, here we are talking about repeaters. These are fast radio bursts which do repeat. There are others where it is uncertain whether they do repeat. They have only been observed once. So the question is,
oh God,
do they repeat if you look at it long enough, or are they just a different kind of bird? And what we found is if you take the energy distribution of these non-repeaters, if you put them all together, you see all this, also this break in the energy distribution. And that is a certain indication that non-repeaters, actually repeaters, you only need to look much longer. And this is why the publication, the title is A Link Between Repeating and Non-Repeating Fast Radio Bursts Through Their Energy Distribution. It's of course not absolutely conclusive, but it is an indication that actually non-repeaters are the same thing. We'll find out more about it, hopefully, as we move on to another fast radio burst, which we have observed again in the same team. The trigger was again a astronomer's telegram by the same Chime Corporation. They said 9 bursts in 3 days and so on. Of course, if they say 9 bursts in 3 days, that's something we really jump to the helm and get our telescopes going. Again, we had a very intensive observation. We had 2,000 some hours of observation time. We have ourselves detected 101 pulses from that, so many more than from the previous FRB. And if you take all together all our telescopes, we had almost 200 pulses. That is. This was an extremely episodic FRB because we had, after we received the astronomer's telegram, we observed in the first 40 days of our observation 83. So of the 101, 83 came in the first 40 days, and then it sort of dropped away. And the last pulse that we had observed was in January of this year. And ever since then, even though we sort of monitor that every now and then, we haven't seen anything again. We're waiting for it to come back eventually, which will be interesting, but for the moment, it's sort of gone. Now, we're still working on the paper for that, but the message is the characteristics, and I'm talking about this break in the energy distribution, very much resembles what we have seen in the FRB that I have talked about before. So it's something that seems to be characteristic of the fast radio burst. So the energy distribution is essentially, the message is higher energy pulses, even though in generally they are less, but they are more frequently than you would expect. And that is again confirmed by this completely different FRB in our second observation campaign. Okay, we are working. Sorry, I did not have shown this. This is again from the same FRB, so it's the same graph here. This is the observation campaign and the number of pulses that we have been observed. You can see there have been very many in the very beginning, and then sort of there's less activity over time. And yeah, the difference here, which I should mention also, is this is the first time that we also had a detection in P-band. There was a single P-band detection, but most of the black lines here are L-band detection. So most of the activity you will find in L-band. And these are the P-band detections. So this is the L-band, and this is the P-band detection. So essentially, you do see them in the L-band, you do see them in the P-band, but the interesting point here is, and that's a remarkable thing, they never occur in both bands simultaneously. So if you have an L-band observation, and one of the telescopes was observing the P-band, we didn't see anything in P-band, and vice versa. If we had a P-band detection, nothing was in the L-band. So this is a takeaway that you should keep in the back of your memory for later discussion. The fast radio bursts that we observe are bandwidth limited. They appear in a certain part of the spectrum at a certain time. They can be here and there in the spectrum, but not everywhere at all the time. Next one up. No, so still, I'm getting confused. That's still on the previous one. So science conclusions so far, very much the same characteristic as in the previous FRB. The break is very similar to the previous FRB. And at the moment, we're presently working on the publication that will again be published in Nature Astronomy. It has just been submitted. And then, of course, then the usual process goes, has to go through a review process, and it will be probably a few months before it's coming out. But the paper is written, which is the main thing. Then next one up, again, same story. CHIME FRB was the first detection, so they sent out an astronomer's telegram. We jumped on it, and we so far have collected about 1,000 something hours of observation time. 70 pulses were detected so far. Combining all telescopes was 160 roughly. And we had one interesting observation by Effelsberg from that. Again, they observed emission in various bands up to 6 gigahertz, but as we found also in our own observation with the other telescopes, the emission was never covering all the band. It appeared here and there and here and there, but never across all the band. And that's something, again, please keep in mind. We also had a session where we did a parallel observation with the X-ray telescope, XMN Newton, a satellite, and to see whether there's concurrent X-ray emission. There was nothing observed so far. And again, this has been sort of dying off, this fast radio burst, because the last pulse that we've seen was in June of this year. The paper on that still is to be written. Also, the analysis, where again we see the same energy break. We have to find out. We'll see. Next one up. Again, our friends at the CHIME telescope, they triggered us and say, look, here's a nice new FRB. That was detected, and we had started the observation in June. I'm afraid there is a typo in the designation here. I need to correct that. I'll put it in the chat later on. So it's a different one than I've been talking about. Again, that we started in June, so very recently. We have 130 hours of observation, but nothing so far. So this is our slight disappointment. Now, the next few slides is something that you would not find in the proceedings, because that's brand new, breaking news. There is another FRB, which this time has not been detected by CHIME, but it has been detected by MERCAT, which is a radio telescope in South Africa. And they reported also via an astronomer's telegram the detection on the 5th of July. And that immediately triggered our observation. So next day we started it. The source has a disadvantage. It has a low declination, which means it is only 4 hours observable for us. So other than that, it's just below the horizon. We have to wait until it's about 10 degrees above the horizon, then we observe, and then until it disappears. So far, we had 8 observation runs, so not that many, with 30 hours of total time until today, including today. And really just in time for this conference, last night we had our first success. So this is obviously not in the proceedings because this event is less than 24 hours ago. And this is what it looks like. This is the detection plot. This is the pulse. And again, this is a representation, and I'll show a bit better of that in the next slide. It's the intensity over frequency. And I would like to take the opportunity here to explain a bit how do we actually detect that and how do we distinguish that from any other pulse. We have lots and lots of pulses, tens, thousands of pulses in an observation coming from radar and all sorts of stuff. And the way that that is done is by really looking at, is it broadband? And the second thing is, does it have a distinctive dispersion? So this is the intensity over time in relation to the dispersion. You can see this is that there's a specific dispersion when all the energy is at one certain period of time. If you move away from that, it gets dispersed. So it sort of spreads out, the pulse spreads out. This thing is called a bow tie diagram. And the way that is done is we have a pattern recognition program, or it's not our program, it's used by the community called FETCH, that uses methods of the artificial intelligence to do a pattern recognition and look for bow tie diagrams. And that's very effective. So we're really able to distinguish between radar pulses and real FRBs. That's a very effective method. Still takes some compute time, but that works quite well. Now, 2 more slides on that. This is a bit more high resolution diagram of that pulse. So you actually can see it's a double pulse. And here again is a bit of a better representation of what we call the dynamic spectrum. So the intensity over the frequency range. Again, our frequency range 1330 to 1430. You again see a certain pattern in here that is due to scintillation, so it gets enhanced at certain frequencies. But other than that, you see a decline over the frequency range, so it gets less to higher frequencies. So it's not quite uniform. So this is really our latest fun piece that we have here. Now, where does it bring us? I talked about magnetars and FRBs, and the big question is there's 2 sides of the same coin? Because many people in the academic environment say they find it likely that FRBs and magnetars are the same. This is very much triggered by a magnetar emission that has been observed a few years ago, which was extremely bright, so that reminded us of an FRB. But indeed, if you look, these are single pulses. Of course, they're indistinguishable if you just look at the pulse itself. Only difference is this one has a much higher dispersion, comes from far away, and this is a local from our galaxy. But still, can magnetars be the progenitor of FRBs? And what I would like to do is to compare a few of the characteristics from our own observation. I talked about episodic behavior, and we find episodic behavior both in fast radio bursts. They come, they go, and the same goes for the magnetar. They come and go, even on similar timescales of months. So that's a thing that looks very much the same. The big difference starts, never ever has anybody been able to find a period in the fast radio burst pulses. Even in the data from the FAST telescope, where they have many pulses in a short period of time, no periodicity was found. And of course, the magnetar, we always see the periodicity, and the single pulses always fit into that period. So yes, magnetars, we know they are rotating devices, just like pulsars, so they have a specific period. Fast radio burst, not yet. Maybe eventually somebody will find something, but a lot of data is available, but nothing has been found yet. The variation in pulse shape, I have not shown much of that, but the pulse shape, there can be sort of all sorts of variations, double pulses, triple pulses, pre-pulses, post-pulses, and whatever. And you find that both in fast radio bursts and in magnetars. Just looking at the variability of pulse shapes, you couldn't distinguish that. You couldn't tell one from the other. I briefly mentioned the set trombone effect. That is the effect that in fast radio bursts, if you have multiple pulses or a complicated pulse structure, they can be, and actually it's quite frequent, a set trombone effect, which is the fact that the first part of the pulse has the energy more in the higher frequency, and that sort of drops down in frequency. And that's called set trombone, because if you try to sort of imitate that, it would be wah, wah, wah. Magnetars, no, we have 100,000 pulses, and we haven't seen any single set trombone. And that goes in line with the fact that the magnetar always, in our observation, has always covered our full frequency band of 100 megahertz. And even the one Effelsberg observation that we have supports that is even much wider. Fast radio bursts can occur also in parts of the spectrum. It can occur in S-band, L-band, P-band, but never, ever all across the spectrum. And I think that's something, again, which differentiates that. So what is the verdict? Are fast radio bursts magnetars? I would say maybe. I'm a bit skeptic. And the skepticism is not shared by too many of the community, but we'll see how it works out. The only thing we can do is do more observations, and that's what we're trying to do as much as we can, having fun with that, and hopefully we'll be able to report more on that story later, maybe next year or whenever we come together again. And thanks very much, and I'm happy to take questions.
Time for 3 or 4 questions online. Anybody?
I'd like to make a comment. I thought it was a very good presentation. I'm just really impressed that this is all done by volunteer people. And my understanding is that somebody has to be at the telescope all the time during those hours of observation. And when you talk about hours of observation, I think those are not continuous hours, they're stretched out. So it really is a big effort. And to consider that it was all done by volunteers and it's really high-end technical work is very impressive.
Yes, that's true. We always have to have an operator on site by our own rules. Technically we could operate the instrument remotely. However, for safety reasons, for the sake of the instrument, we always have the strict rule: somebody has to be on site. And as you can imagine, that's thousands of hours with somebody sitting there and babysitting the instrument. And unfortunately, that's not always daytime. At the moment, the one that we have just observed last night, somebody was sitting there in the middle of the night until 2 o'clock in the morning our time, because it's only above the horizon at this time of the year during the night period. So a lot of red eyes are needed here and there.
Yeah. I wanted to ask,
Speak up.
Dr. Herrmann, had your colleagues also witnessed the last night's FRB as well?
I don't know yet. We have a sort of internal discussion, and typically we are a bit faster in evaluating our data. According to the plan, it might be that Westerbork might have been on source during the night, but they were sharing time between various targets. So I'm not sure whether they actually have been on target. That question has obviously been asked, but I don't have an answer yet. Hopefully somebody else was on source, and ideally on a different frequency band. So, for example, if Torun had been on source in S-band, that would be interesting to see whether it has occurred or not occurred in S-band.
Okay, thank you very much, Dr. Herrmann. Wonderful presentation.
Okay.
We do have one more comment from here.
Can you hear me? Hey, can you hear me?
Yes, you should be heard. Go ahead.
Yeah, so considering the dispersion and the average electron density between galaxies, based on your measurements, how far do you think the FRBs are coming from? Dr. Herrmann?
I'm not sure if you heard the question, Dr. Herrmann. He was asking, is there an estimate on the distance to the source for the FRBs?
I see Wolfgang's mic is muted. He might have stepped away.
Okay. All right. We'll move on then. Thank you again, Dr. Herrmann, if you're hearing us.
I'm sorry.
Mhm.
So I understand there may be another question or comment.
Yes, we had one question. Do you have an estimate for the distance to any of these sources?
Yes, we do have actually a fairly accurate distance for two of the FRBs. Those are the first two that I have mentioned, because they were localized by interferometric means. So the host galaxy is known, and if you know the host galaxy, you can determine the redshift, or the redshift of the galaxy is known. For the first two, we are talking about roughly 1 billion light years.
Okay.
And so the B,
Okay, thank you very much. Any further questions, please post them in chat. And if Dr. Herrmann has time to stick around and watch the chat, perhaps we'll be able to have an online conversation that way. So thank you again, Dr. Herrmann.
Thanks very much. I'll certainly look at the chat.